The third video in lesson 3.2 is on evaluating logarithms involving common logarithms. Now, common logarithms are one of the most common or popular logarithm base to use. A common logarithm is a base 10. Because the base 10 logarithm was commonly used, they most of the time will not write a log base 10. So if you have y equals log of x, it's the common log of x, and they will not write, although you could, it means the same thing as log of base 10 of x. But they shorthand it, you know how they always try to write it in the simplest form. Since it's used so often, since it's a common logarithm, they just simply write log of x. So anytime you don't see it, it's a log base 10. The next thing that they kind of emphasize here is the relationship between the log and the exponential format. So what we're seeing here is an if and only if statement. This is the definition, how they're related. If y equals log of base 10 of x, or if y equals a common log of x, it's only going to be true if and only if we want to rewrite this using an exponent, the base on this logarithm is 10, so the base on the exponent is 10. The logs always equal the exponent, so the y is the exponent, so y goes in the exponent spot, and the x is in the antilog spot. So here's the relationship relating the two forms back and forth to each other. Same thing as we've been looking at. The only thing that's different is base 10. In the previous slide, we had basic properties of any base logarithm. They're doing them for common logarithms. I'm not sure why this is so valuable, but here's what they're saying. The common log of 1 equals 0 because, well, the same reason we did on the other. Since this is a base 10 number, we can change it into an exponential, and it's 10 to the 0 equals 1, and therefore we've got a true statement where 10 to the 0 is 1 equals 1. So that works for a base 10 number, for base 10 logarithm. The next one is the common log of 10 is equal to 1. Again, remember, common log is a base 10. If we rewrite this using exponents, it says 10 is the base of the logarithm raised to the exponent of 1 has to equal our antilog, which is 10, and 10 to the first is 10, so that is true. The next example is, or property is the log, common log of 10 to the x equals x. Nothing new here. Again, we're just reiterating what we did in the previous video, that if I change this to the exponential, the equivalent exponential is it's got to have a base 10 exponent. The logs always equal exponents, so 10 to the x has to equal the antilog, which is 10 to the x, which is a true statement. And the final one is 10 raised to the log of, common log of x equals x. And this is a base 10 logarithm. But this time it's written as an exponential format, so I'm going to change it into a log format. So if I go into a log format, it has to have the same base as the exponent, which was 10, or a common log. So the common log of 10 equals, the logs always equal the exponent. Here's the exponent, log, base 10 of x. And this is your antilog, and the antilog always goes on the argument of your logarithm. So here's the three same properties, only in common logarithms or base 10 logarithm. Another point of emphasis I want to make here, this red graph, I graphed it earlier in the presentation, that is y equals 10 to the x. One of the things I want to reemphasize on this, and I didn't do it the first time because I wanted to wait until I got to these problems where it made a difference, is that if you think about the domain of an exponential function, the domain is going to be all real numbers. But if you look at the range of these numbers, the range of all exponential functions are all real numbers greater than 0, or a lot of times they'll say it's all positive real numbers. If you think of your interval notation, it's everything from 0 to positive infinity. Then I graphed the inverse function, which is the logarithm, or the common logarithm of 10. So this one is y equals the common logarithm of x, which means every ordered pair from this one has to get turned around to graph this one, and that's what's happening here. It's the ordered pair that was 0, 1 becomes 1, 0. The ordered pair that was 1, 10 that's up here becomes 10, 1 out here. And the ordered pair that is at a negative 1 should be 1/10. That ordered pair gets turned around as an ordered pair, and it's 1/10, 1. So go to 1/10 and negative 1 should be 1/10, negative 1. So 1/10's got to be somewhere in here. So it's the order pair 1/10, negative 1. So here's what I want to emphasize. This is our inverse function graph, and because it's the inverse, the domain and the range of our inverse function have to get turned around just like our ordered pairs get turned around. So the domain of a logarithm function is the range of the exponential function. So it's going to be transferred as all positive reals, or if you wanted an interval notation, it goes from 0 to infinity. And that's what this green graph is kind of emphasizing. All we can put in are positive real numbers. You can't put in 0 and you can't put in negatives. And then the domain gets flipped to the range, and the range can be all real numbers back out. We get both positive values of y and negative values of y. So you got negative values of y there, positive values of y here. So whenever we look at these, we know that the logarithm will be the inverse of an exponential, which means the domain and range gets turned around, which is nice to think about in this technology study tip. If you try to take the common logarithm of a negative number, your calculator will display error, non-real answer, or an imaginary number. That's because of this domain restriction sitting right here. So what I want to reemphasize is you never can take the log of a negative, because logs of a negatives are undefined in their domain. So we got to keep that in mind as we try to evaluate. So we're going to use some of these exercises are going to be calculator exercises, and others are going to be without a calculator, and we're going to kind of ebb and flow in between these. So the first one says, find the common log of 10,000. Now the common log is a base 10. It's saying, find the exponent I raised 10 to get 10,000. Well, since the bases aren't aligned, and this one's pretty simple to do, it's 10 to the x equals 10,000 is 10 to the 4th power, therefore x has to be equal to 4. The exponent that we raised 10 to get 10,000 is 4, and that's exactly what this statement is asking to find, that exponent. Okay, so that one you can do without the use of a calculator, no problem. In example 3b, take the common logarithm of 0.081. Now this is a log of base 10, so 10 raised to some power has to give me 0.081. Now that one is a little bit out of control here, because there's no way we're going to change a 0.081 into a base 10 number without the use of technology. So here's what we're going to do. We have a button on this calculator, and since this is not one of those formats where we can do this and change base, we're going to strike that off, and what we're going to do is just use our graphing calculator and our log button. And it doesn't matter, you can have any scientific calculator, it should work. As soon as we look at and hit this log button, that's the same thing that they've got up here in our question. Take the common log of 0.081. And if we hit this, and what it's telling the calculator to do is, go find the exponent that we raised 10 to get 0.081. Just like this statement here that I'm telling you, that's what it's going to find. So if I hit enter on this, it's going to be a negative 1.09 approximately. So x is approximately negative 1.09 with some other stuff following behind it. Okay, so what's kind of cool on this is, if this is the exponent that I was supposed to get, then when I raise 10 to this power, raised to the power of the answer, so I get the whole fraction, the whole decimal number in there, hit enter, look at that, you get 0.081. So we really did find the exponent. We raised 10 to get 0.081 or 81 thousandths. Okay, so letter C. Letter C, it says, find the exponent that you raised 10 to get a negative 0, which negative 0 is kind of funny in the first place. There is no such thing as a negative 0. 0 is neither positive or negative, so what about 0? So what is the exponent I raised 10 to get 0? That's what this statement is saying. Find that exponent. Logarithms say go find exponents, and 10 to some power has to give you 0. Well, what power can you raise 10 to get 0? I want to relate that back to an exponential function. Is there any way that I can take 10 to a power and get it to equal 0? And that has to be false, because there's no way I can get 0 out of an exponential function. It comes close to 0 but never touches it. So because this is a false statement, that means this has to be impossible to solve. And really what we're saying is, can we take and find the log of 0? No. That's what the discussion back up here was when I did these graphs. This domain on this green function has to be any number greater than 0 all the way to positive infinity. Well, 0 is not bigger than 0, so therefore if we try to take the log of 0 on our graphing calculator and just try to double check ourselves, you take the log of 0, parenthesis, equals, and it gives you a domain error, which should make total sense because it's out of our domain of our logarithmic function. So the golden rule is never take the log of 0 or negatives or any number that is not positive. You have to take logs of positive numbers. And then in the fourth example, 10 raised to the log of base 10 of 3. I'm just going to put that base 10 in there for the common log. It's an exponential base 10 and a logarithm of base 10. These are inverse functions that should undo each other, so we should just get 3. 3 is the exponent that we need. And another way of thinking of this, come back to it, it's 10 raised to the log, common log of 3. It's saying, what is the exponent I raised 10 to get 3? This says, what is the exponent I raised 10 to get 3? So 10 to some power has to give me 3. I got to go find that exponent. So I'm going to go find that exponent. What is the exponent I raised 10 to get 3? Well, the easiest way to do that, let's get rid of that. It's clear. Take the log, common log of 3. Well, that's 0.477. 0.477 is the exponent I'd have to raise 10 to get 3. So now let's take a look. We've gotten this exponent. It is 1 or 0.477 and so on. So this is this 0.477 number approximately. But then I got to turn around and take 10 to that power. So if I take 10 to that power, so what happens if I take 10 and raise it to that power that we just found in our answer? It better give us right back to 3. And the final little connection to this, there was a property on this that says if you have 10 log of base 10 of 3, this has to be equal to, this is written as an exponential, so I could write it as a logarithm. It's the log of base 10, just like the exponent is, has to equal, the log of base 10 of the argument, or the antilog, which is what we're going to find, because logs always equal the exponent. Here is our exponent, log of base 10 of 3. What is this anti-logarithm that would make these two statements equivalent, and that is when x equals 3. So I like to try to hit that one in as many ways as I can to have you think through it. Hopefully one of those 3 really connects with you and resonates so that you can remember how to evaluate those. But those should be really quick and easy because they're showing you inverse functions or operations right away.